Good afternoon, all. This is Ted Welsh, the Director for the Defense Systems Information Analysis Center. I'd like to welcome you all for joining us in the latest of our webinar series presentations. Just want to take a quick minute up front to give you an overview. Hopefully, most, if not all, are aware of what the Defense Systems Information Analysis Center provides, but just in case you aren't, again, DSIAC, or the Defense Systems Information Analysis Center, reports up through the Defense Technical Information Center, ultimately to the Undersecretary of Defense Research and Engineering. We operate as a government-owned, contractor-operated entity, supporting the bench scientist 6.1 activities up through the warfighter 6.3 activities, principally in terms of advanced technology identification. And in that context, the primary mission areas that we have are oriented towards collecting and curating scientific and technical information, conducting information research and analysis, and dissemination of scientific and technical information, for which this webinar series is one of those products that of a number that we perform to help promote information sharing, collaboration within the defense systems scientific and technology community. So again, these webinars hopefully promote an awareness, a greater understanding of our role. We provide a variety of services and products, and again, host a website where those all can be accessed, and a greater awareness can be found if there's not already, and that's the DSIAC.org website. I welcome you all to check that out if you haven't already. And with that, I will go ahead and turn over the proceedings and the mic to our presenters. And again, this webinar is entitled or orchestrated towards dealing with UV light, specific wavelength of UV light for continuous disinfection for occupied buildings and vehicles. So again, with that, I'll turn it over to Jamie and PJ, who will be your presenters today. We will have a Q&A session at the end, and you can kind of chime in with Q&As via the chat, and I'll keep track of them, and we'll facilitate getting them answered at the end of the briefing. Thanks.
Okay, so this is Jamie Childress. I'm with Boeing Research and Technology, and I, along with my cohort, PJ Piper from Far UV Technologies, are going to be talking to you today about 222 nanometer ultraviolet light for continuous disinfection. And I'm going to talk to you, I'm going to give the first part of this, which is about 222 nanometer technology. And then PJ is going to take over and talk to you about various applications. So Sharon, let's go to chart 2. So the bottom line here is that 222 nanometer UV is both safer and more effective than older systems. So let's say the older systems are the longer wavelength systems, which include mercury lamps and longer wavelength LEDs. And so 222 actually will allow continuous disinfection in occupied areas, which is not possible with older UV systems. And since I like to kind of give the bottom line up front, the why is because 222 is highly absorbed by both protein and DNA, and the older UV systems are really only absorbed by DNA. And you're going to see in a little bit that makes a big difference. So Sharon, let's go to slide 3, please. So this is a very brief history of UV disinfection. UV light has been used for germicidal purposes since the 1930s, and back in the 30s, it was discovered that mercury lamps had germicidal properties, and then over time it was discovered that it was very specifically the 254 nanometer light frequency that came from those mercury lamps that was giving, killing viruses and bacteria. And so as a consequence of that, and that has been around since the 1930s, almost all of the data that you see actually on germicidal properties of UV is very specifically the germicidal properties of 254 nanometer light. And then in relatively recent years, LEDs have come along that emit useful germicidal frequencies between 260 and 280 nanometers. And those LEDs in the 260 to 280 nanometer range have very, very similar properties to 254. So that you can sort of think of that sort of 254 to 280 nanometer range as being all more or less the same sort of flavor of UV, if you will. Then only very recently, really, has there been sort of a new flavor. So you can almost think of that 254 to 280 nanometer range as being sort of vanilla UV, if you will. And so the new, Ben and Jerry's, chocolate extra special UV is now this 222, which is a completely different frequency of light. And so let's go to slide 4. And we'll give you sort of a little better overview of the electromagnetic spectrum here. So as you can see in slide 4, the ultraviolet light is to the left of the visible spectrum. And so it's, this kind of goes without saying, but just to make sure everybody gets it. So ultraviolet light is invisible. So all of these light frequencies that we're going to be talking about are invisible to humans. But even within this ultraviolet band, not all light is the same. So there's, essentially a spectrum of ultraviolet light, and that spectrum is divided into UVA, UVB, UVC, and far UV. And so UVA is essentially what people normally refer to as black light, so kind of your black light poster sort of light. And it's very close to visible light. UVB is the portion of sunlight that gives you a sunburn, and so UVA and UVB are present in sunlight. When you get down to UVC, which begins around 280 nanometers, that's no longer present in sunlight, and that's one of the reasons why it is germicidal, is because microbes haven't developed defenses against it since it's not normally present in sunlight. So mercury lamps are at 254 nanometers, and so if you're not familiar with nanometers, it's essentially the length of the wavelength. And then down in the far UV range is the 222, and so that's what we're going to be really focusing on today, is 222 and how it's different from existing wavelengths. So let's go to slide 5. And one of the reasons that you're probably not familiar with 222 is that 222 Eximer lamps are a pretty new thing. And actually making UV light in general is actually not that easy, at least not the germicidal wavelengths are not that easy to make. And in the particular, 222 is something that's only been able to be made, in a sort of a semi-efficient way fairly recently. And the way that you make them is with an Eximer lamp. And an Eximer lamp is essentially a glass bottle filled with gas and lined with high voltage electrodes. And then a lightning storm effectively is precipitated in that lightning bottle. And so there's a high voltage lightning storm that discharges between the inner and outer electrodes. And that discharge actually creates a temporary molecule. And it's that decay of that temporary molecule that actually creates the light. And now Eximer lamps can be made with lots of different kinds of gases, and the gas that is in the lamp actually determines the light frequency that it generates. So it in the case of creating 222 nanometer light, a mixture of krypton and chlorine gas will emit 222 nanometer light with this high frequency lightning storm in the bottle. So if you look at the graph on the right, you see the wavelengths emitted from a krypton chlorine gas filled Eximer lamp, and you'll see that the preponderance of the light that is emitted is at 222, but there is some amount of light that is emitted at higher frequencies, at the, say, 240 to 260 nanometer range. And those are actually undesirable frequencies because those frequencies could give you cancer. So typically for the 222 nanometer systems, we also add a low pass filter to the lamp, and that cuts out this small portion of light that is emitted in those higher wavelengths, and that's kind of important to do. There are such things as 222 nanometer LEDs, but they're only really in research. There's no mass production of 222 nanometer LEDs. And the 222 nanometer LEDs that are in research, they're very, very low efficiency. So their efficiency is typically less than 1%, and pretty often much less than 1%, so a very tiny fraction of 1% actually. So you can think of like 222 nanometer LEDs as really more like a small electric heater that happens to emit a small amount of 222. So it's difficult to make, but there now are commercially available 222 nanometer Eximer lamps, and so we're going to take advantage of that. So let's go to slide 6, and this is going to help explain why we are interested in using 222 as opposed to 254 nanometer mercury lamps or the similar LEDs in the 260 to 280 nanometer range. So really, I'm just going to focus on the graph on the right-hand side of this chart. The horizontal axis of the graph there at the bottom is wavelengths, so wavelengths of light in nanometers, and then the vertical axis is the absorption of those wavelengths in two different molecules. So the blue line is DNA molecules, and the green line is protein molecules. And so if you let's look at the 254 nanometer line there, which is the red line, and you'll notice that it intersects the blue DNA line pretty high up on the graph. So it's got so DNA strongly absorbs 254. But it intercepts the protein line very low in the graph, so protein doesn't absorb 254 very readily. So it pretty much passes through protein without too much trouble. Now, if we look at the 222 nanometer line, we'll see that the 222 nanometer wavelength is very highly absorbed by both DNA and protein. So it's got sort of a similar absorption of DNA in DNA, but it's much higher absorption of protein than 254, and so that actually proves to be a really important thing. And so really the key takeaway from this slide is that protein has 25 times better absorption of 222 compared to 254, but the DNA absorption is similar. So protein is highly absorbed by only 222 really of those two frequencies. So let's go to slide 7, and you'll see why this matters. So the bottom line of why this matters is because all cell walls are made of protein. So and that's the cell walls of viruses and bacteria, or the cell walls of any part of yourself is made of protein. And so that means that skin is mostly protein, actually. And so what this, so the graph on the left-hand side of this chart, again, the horizontal axis is wavelengths, so UV wavelengths in nanometers. The vertical axis is the the opposite of absorption, which is transmittance. And let's look at the lines on the graph here now. So the green line on the graph is the transmittance for all these different wavelengths of the stratum corneum. And the stratum corneum is the outer layer of your skin. So the stratum corneum, you could sort of think of that as sort of like the bark on a tree, only it's the bark on your skin. And the stratum corneum is a dead layer of skin on the outside of you, and it's this dead layer that allows you to scratch the back of your hand without bleeding, because since it's dead, there's no live cells there, and it's constantly being sloughed off of your body. And if we then look at the next line, the purple line, the purple line below the green line is the penetration of different wavelengths through the epidermis. An epidermis is another outer layer of your skin, and it's essentially the last layer of your skin above the portion of your skin that's actually creating new cells, which is our basal cells. And so really ultimately the goal is that you have, if nothing penetrates the epidermis, then you're good and you can't get cancer. So now let's look at 254 nanometers, which is there's an arrow there pointing to where that passes through each of these lines. And about 50% of 254 nanometer light makes it through the stratum corneum, so essentially makes it through your bark. And around 3% of it makes it through the epidermis. And so it's that 3% that makes it through the epidermis that causes the trouble. So that 3% making it through the epidermis into the basal cells gives you a skin cancer risk of, if you had chronic exposure to 254, of about 1 person in 3,000. And so it's this skin cancer risk of 1 person in 3,000 that means that older UV technology, so 254, and which you notice that if you look at the graph in there, the 260 to 280 nanometer range, again, it's sort of similar numbers, right? So any of those wavelengths, whether it's a mercury lamp or it's UV LEDs, all of those wavelengths are capable of giving you cancer in approximately that range. And so you cannot really use them in an occupied area. So for you to disinfect an area with either mercury lamps or UV LEDs, you really need to remove all the people from that area. So now let's look at 222. So if we look at the vertical blue line there, which lines up with 222, we see that only about 0.03% makes it through the stratum corneum, because of course the stratum corneum is mostly made of protein, and because 222 interacts highly with protein, it doesn't really make it through that very well. And roughly 0% makes it through the epidermis. And so your skin cancer risk is actually less than 1 person in a quadrillion. And I think I checked last night, and there's something like 7.9 billion people on the planet, which is considerably less than a quadrillion. So that means that 222 is actually very, very safe from a standpoint of giving you cancer. In fact, if you see as noted on this slide, 222 UV is actually considerably safer than sunlight, because your risk of cancer from sunlight is much, much greater than that. So let's go to slide 8. So there's been quite a lot of safety data that have been collected on 222 nanometer UV just in the last few years. So again, it's only very recently that really 222 nanometer UV has been commercially available. So 222 Eximer lamps. So since it's only very, very recently that's been available, the data on it is fairly new, but that data is all pretty consistent, which shows that it's very safe. It's very safe for humans, and those studies support raising the human daily exposure limit with the TLV to well over 500 millijoules per square centimeter. And for those of you who don't speak millijoules per square centimeter, that is a measure of the energy, the total energy of light that's been deposited on a surface, both by the intensity of light as well as the amount of time that went on. And so 500 millijoules is actually quite a lot of light. And so human and animal skin tests up to even 1,000 millijoules have been done with no adverse effects. Animal eye tests have been done up to 600 millijoules with no adverse effects. And one of the reasons that this is the case is that there is a layer sort of similar to the stratum corneum on the eye called the tear layer, which is essentially the outer protective layer of the eye. And so that also basically absorbs the 222 before it can damage anything in your eye. And one thing to keep in mind with these numbers, the 1,000 millijoules and the 600 millijoules, is those were not where, let's say, damage started. That was actually the maximum value in the test. So we don't actually know what the upper limit is because that would just happen to be the limit that was used in the test. So we don't really know what the true upper limit, if in fact there is an upper limit. So another test that's very, very interesting is Columbia University has been doing a testing of Dr. David Brenner on hairless mice. And he is concluding right now a 60-week study of hairless mice. And a 60-week is literally the lifetime of these mice. So at the end of the 60 weeks, the mice are essentially geriatric mice. And then those mice were exposed for 8 hours a day, 5 days a week, to 500 millijoules per square centimeter, and for their entire life, and with no adverse effects detected. So the postmortem autopsies and pathology on that are in process, but it is anticipated that there will be no damage detected from that analysis. In the lower right of this chart, you see yet another graphic example of the difference between, say, 254 or older UV lights and 222. The horizontal axis is in millijoules per square centimeter, again, which is essentially you could think of that as the dose of UV light, so it's the total energy deposited. And in the case of 254, you'll notice that the cell DNA damage, as defined by the CPDs, which are essentially lesions on the DNA, so DNA damage. You notice as the total energy goes up, the DNA damage goes up. So quite a lot of damage is created. In the case of 222, which is along the bottom of the chart, even as the fluence goes up, there is really no change from zero. So again, further evidence that 222 is relatively harmless to humans and potentially completely harmless to humans. So let's go on to chart 9. So chart 9 really shows us the kind of what the regulatory situation is, and 222 is regulated by the EPA as a pesticide device, and no FDA regulation is required unless it's used as part of some kind of medical treatment of some sort. And most people, most organizations follow the ACGIH, which is the American Conference of Government Industrial Hygienists, threshold limit value for particular UV wavelengths, which is also known as the TLV. And so in the right-hand side of this chart, you see a graph showing the TLV for a wide variety of UV wavelengths. And you'll notice that 222 is only at 23 millijoules per square centimeter, and but yet we have plenty of data showing that even more than 500 millijoules appears to be completely safe. And that's just because since 222 lamps have really only been commercially available for a short period of time, this 23 millijoules number was based upon an extrapolation of other UV, effectively other UV wavelengths, extrapolating out through 222, and so it was not based upon clinical studies. And so there's a fair bit of effort right now going into revising this TLV, and it is hoped that fairly shortly, later this year, that the TLV for 222 will be raised into that sort of 500 millijoule per square centimeter number. So although the TLV for 222 is already higher than it is for, say, 254, so 254 is only 6 millijoules, and say 270 nanometers is only 3 millijoules, so it's already considerably higher, but the word on the street is that it's going to get considerably higher, much more into the 500 millijoule type number later this year. So let's go to slide 10. So as we've seen, 222 is fairly harmless to humans, but is it also harmless to pathogens, or is it deadly to pathogens? And it turns out that it's quite deadly to pathogens. And the reason that it's deadly to pathogens but harmless to humans is because viruses and bacteria are really, really tiny. They're orders of magnitude smaller than human cells. So to put that in scale, so viruses are typically in the 100 nanometer diameter range. So specifically, let's say the SARS-CoV-2 virus is roughly 100 nanometers in diameter. Bacteria, so 100 nanometers is 0.1 microns in diameter. Bacteria are at 1 micron in diameter roughly. And whereas human cells are more like about 40 microns in diameter, and 222 nanometer UV is typically capable of penetrating, say, 3 to 5 microns into a protein. And as we mentioned earlier, all cell walls are made of protein. And so in the case of a human cell, actually 222 UV cannot even really penetrate into the center, into the nucleus of a single human cell, much less through your skin. But it can fully penetrate viruses, and it can fully penetrate bacteria. And since it interacts with both protein, which essentially the viruses and bacteria are made of protein, as well as DNA, it destroys both their DNA and their protein. And because it's destroying both their DNA and their protein, and they don't have a thick protein shell, unlike us, that is very effective. So if you look at the picture in the lower right, you see this is a coronavirus. It's the CoV OC43 coronavirus, and even a very small dose of 222 is capable of defeating this virus. So even a fraction of a millijoule. So kind of compare that to the, say, more than 500 millijoules that would be safe for a human. And you can see that you can very easily kill things when humans are present. So let's go to slide 11. And because everybody's, of course, very, very interested in the SARS-CoV-2 coronavirus, because it's responsible for COVID-19. So the required UV dose for a 99.9% surface disinfection of SARS-CoV-2 is roughly 6.5 millijoules per square centimeter for 254, but only 3 millijoules per square centimeter for 222. And although it's, we don't have some, exact studies of indicating exactly why 222 is so much more effective, but it's because of the protein interaction, it's likely that it is due to the fact that the SARS-CoV-2 virus, as well as pretty much all viruses, have a protein outer shell, and so that interaction with protein is probably has a substantial amount to do with why it's so much more effective. So bottom line, I guess, takeaway from this is that 222 is at least as effective, if not more effective, than 254, but it's considerably safer. So let's go to slide 12. So this is kind of my last text slide, and then we'll move over to the applications. So the kind of last thing about 222 that is of note is that because of that protein interaction, it's not subject to a thing called photoreactivation. So both 222 as well as the 254 or the 260 to 280 nanometer UV damage the DNA of the target organism. That actually does not kill the virus or bacteria. It actually simply inactivates it. Because the DNA is damaged, the pathogen cannot reproduce itself, but it is still alive, so it's just inactivated. So inactivation essentially means it can no longer replicate itself. So photoreactivation is actually a repair mechanism that quite a number of microbes have that allows them to repair that damage if they are subsequently exposed to blue light. So if you expose pathogens that have what's known as a photolase gene to UV light, and their DNA is damaged and they're inactivated, if you subsequently expose them to ordinary light, so that includes blue light, it will actually reactivate them, and so although you may think that you have disinfected that area, the area will become essentially reinfected within just a few hours after your exposure to ordinary blue light. So 222 appears not to be subject to photoreactivation, and the assumption in there is that that's due to the fact that not only has DNA been damaged, but also the cell wall of the pathogen has been damaged, and so the viruses or bacteria are truly killed. So they're not simply inactivated, they're actually killed. So let's go to slide 13. And so I'm not going to really cover much in the applications because PJ is going to do that. But suffice it to say that it is highly effective for disinfection as well as safe for people, and you can use that in either high-powered applications, or you can have some kind of automatic disinfection of occupied spaces. And so now let's go to the next slide, and PJ can take it away. So PJ.
Hi, thank you, Jamie. Yeah, well, that was a lot of great data. And in fact, as I was watching through, I was kind of thinking of a few notes. Everybody loves kind of big numbers, but sometimes they're really hard to comprehend. And when you talk about a quadrillion, it really kind of goes off the charts. I tried looking up something after that ASP, American Society for Photobiological presentation, that chart that you showed, and tried to find other examples of remote possibilities. And it turns out, if that chart holds true, which of course it's extrapolated and very far, it would imply that it's a billion times less likely to get skin cancer from far UV than either winning the lottery or potentially, according to NASA, the Earth getting hit by a 5 to 15 kilometer wide asteroid that would be an extinction event. So it's pretty amazing stuff. In addition, well, I'm going to talk a little bit about the applications, but I did also want to just kind of touch on the why, because a lot of people have asked, hey, with vaccines, is this really necessary to outfit our facilities? And another interesting fact is that throughout recorded history, more than 1 in every 3 people have died of infectious disease. So while COVID has been horrible and has taken 500,000 lives, as we look at the market right now in the U.S., in terms of big numbers again, what we're really hoping to impact with far ultraviolet light disinfection is potentially save 100 million lives. And so it's a significant play. I think the other aspect that's often missed in this is that, and you touched on it when you were talking about how it really is agnostic to the pathogen treated. So regardless of the virus or bacteria, it's gonna attack foodborne illnesses, E. coli, Salmonella, Listeria. It's gonna address hospital-acquired infections like C. diff or MRSA. And it's interesting. I mean, it really boils down to really any of the pathogens, even mold or fungus, or even the common cold and flu. So I think this really is a solution to one of the most vexing problems we've really had through human history. But as far as the solutions go, if we can move to the next slide, I'll start to kind of talk about some of the places where we have been where it's been utilized. Really, far UV is best utilized in any higher traffic, higher risk area, and in theory, it could really be used in any occupied setting as safely and effectively as Jamie pointed out. There are still cost impacts, and I think what's happening now is as the volumes are increasing, the costs of this technology are going to continue to come down, and it's going to make it more and more readily available and more, a place where you can put it anywhere. And most importantly, what's neat about far UV is unlike other disinfection options where you're totally reliant on a human input, like wiping surfaces down or spraying things with chemicals and adding, kind of an environmental challenge into the area. It's really independent of that. And so it's autonomous and it's continuous. And if you can see in the picture on the left, right under the facilities, you can basically see what a lot of these devices are. They're ceiling fixtures in many applications, which are set it and forget it solutions. And, by the second day, it just appears like a smoke detector, and it's kind of a boring solution, but it is cleaning most of the air and the surfaces in that room, and in particular the surfaces it touches. So it's a line of sight disinfection. So it's not going to treat under that counter that you can see on the right side of that picture on the left. But the part that people touch is generally the top of the counter. It's not the bottom. And if you think about the contamination events that occur with a respiratory disease, 100% of those contamination events happens when a person breathes, talks, coughs, sneezes, or sings. And the heavier particles fall relatively quickly to the tops of whatever the surfaces that are below that event. And then medium-sized ones fall a little bit slower, but they eventually all succumb to gravity. The lightest particles actually can float around for hours. And so the concept of social distancing can be a little challenging when you all walk through the same door, right? So if that's going to float around that doorway for 2 to 3 hours, that's, can be challenging. And so a question we always get asked is, well, hey, when do I know it's safe to take my mask off? And I think we're going to be facing this question for more than a year. I think, there are several it's been commonplace for people to wear masks for many years in Asia, and I think that's because a lot of these outbreaks that have happened have made it clear that these things are happening more often. If you look at the history of SARS, MERS, Ebola, these things are hitting almost every 3 years. So in theory, the next one should be due in 2022, which is just next year. So we don't know how wide it'll spread, but I think a lot of the defenses that we put up are going to substantially mitigate that. But one interesting thing about all these defenses, whether it's social distancing, face masks, hand hygiene, or vaccines, is they're all just additional layers of defense. And they do nothing to actually reduce the viral load that's in the air or on the surfaces around you, whether it's COVID or whether it's the flu or regardless of what it is. And so I think what we're able to offer with far UV is now a solution that's actually playing some offense. To borrow from a sports analogy, sometimes your best defense is actually playing pretty good offense. And I think a lot of the data that Jamie showed out there is right that. And in application, again, it's pretty simple to install. It takes about 10 to 15 minutes to install, a ceiling fixture. Any electrician can do it. The next panel over is for airplanes. And I think this is a very interesting case. So we are working under an AFWERX SBIR and with Little Rock Air Force Base in particular. And, we've been looking at the planes and we've been looking at cockpit disinfection. If you think about a cockpit, and you can see the picture above is kind of a higher powered wand version. It's very hard for a person, again, this gets into the human error issue, a person to clean 500 knobs with a disinfecting wipe or something like that. It's literally almost impossible to do. And, with a higher powered bulb, now the higher powered bulbs will exceed the TLVs, so you would need PPE to wear, and you can see the woman there is wearing, gloves and, basically long sleeves. It's not like a hazmat suit or anything. But that device can actually disinfect those surfaces in less than a second, up to a 3-log kill, up to 99.9% of certainly the SARS-CoV-2, and really at that power, almost anything that's really going to be on there. In terms of the different types of viruses, there's actually quite a bit of information out there. While this has been researched, like Jamie mentioned, by Dr. Brenner at Columbia for quite some time, probably almost 10 years at this point. It's really been picked up by the others. So Dr. Sliney and Johns Hopkins with, the standard setting organizations, Harvard Medical School, Colorado, universities in Scotland and Japan and really across the world. So I don't think this is really as much a novel thing at this point. I think that the safety and efficacy has been proven. And now I think what we're really going into is a lot more of this applications development. How can we use it? How can we rapidly deploy it? And so there's a couple other applications. So the airplanes right now, one of the challenges is it takes longer to get something, certified for use on an airplane. But going in between flights and cleaning is very straightforward. There's not additional requirements there. So that's a great application for a wand. Airports, if you go through the Atlanta, airport and the Delta terminal, you'll see far UV there too. So it's spreading. From actually the defense was one of the first sectors to really kind of pick up and start using it. And half these pictures are really taken from some of our installations, at Air Force bases. It's even used at the highest levels of the Pentagon now too. So this is not, as much as far UV is agnostic to the pathogens are really agnostic to any people catching this too. So regardless of your gender, your age, your ethnicity, or where you are, this is both a defense and a civilian need. You can see that in the far right here, there's also its use in mobile settings. So just as, you could be, crowded in the hallway, shown on the picture on the left, you could also be getting onto a bus with multiple people. And so, fortunately, a lot of these devices are powered with low voltage DC, so it's very easy to connect into those mobile applications as well. And there's even, just completely mobile and immediately deployable floor lamps available too. As you start to think forward, though, it's really any place where people congregate, those higher risk, higher traffic areas where you'd want to consider these. So we're also seeing a lot of uptake in dining facilities, athletic facilities. Think of any of the places where you would take off your mask. One of the interesting studies that came out probably about 3 months ago now was actually they did the studies that looked at the computational fluid dynamics of the particles that would be in the air going around the room and the impact of far UV on that. And it demonstrated that utilizing far UV in an occupied indoor environment is equivalent to providing an extra N95 mask for everybody in those spaces. So if you're dining and you have to take off your mask to eat, or you're playing athletics and it's not exactly easy to wear a mask during that, having far UV still allows you to have the same effective support. But even above and beyond, if it's continually disinfecting, it's getting rid of the viral load completely. And if you don't have the viral load, you can't get infected. If there isn't any present pathogen to infect you, that's a true sign of safety. So logistics support, there are national stock numbers now available for any of these devices. So they are readily available without contracting issues. Some of the early efforts we had to rely on sole source SBIR designation and things like that. But now with national stock numbers, they're readily available. Commissaries, secure rooms, common sleeping areas. These are all areas where if there was one infected person, they could be spreading it through the air or on the surfaces that they might touch. And then I just have one more slide of a couple more applications, if we can move forward to 16. So these are other areas that, again, that we're touching on, and a lot of them are defense related. Most bases have visitor centers, conference rooms, auditoriums. Haven't seen as many offices elevators on the bases, but, that is an area where there isn't really even HVAC. And HVAC is an interesting question too, because somebody is, there's been questions around the cost effectiveness. And there's some interesting studies out. Actually, I think it was on a recent webinar that showed that they were analyzing the differences between ventilation and UV disinfection, and I guess it's 9.5 times more expensive just to ventilate the conditioned air out of your building versus using an ultraviolet light solution. And so that's a really interesting case, because a lot of people have thought, well, hey, I'll just get all fresh air and that'll be a lot cheaper than installing far UV lights. But in fact, it's exactly the opposite. It's a lot more expensive to blow that conditioned air out of your building. Similarly, to say, oh, we're just going to have somebody go in and wipe stuff down has turned out to be 50 to 100 times more expensive, on a daily basis. It can be less than a couple of dollars to disinfect your space over the life, 1,000-day life or something of one of these products, versus paying somebody minimum wage even for 10 hours on a daily basis to go around and clean this. Other applications, bathrooms, recreational areas, a lot of healthcare. In fact, most of the initial calls were from healthcare providers, because 70% of all hospital operating rooms have already utilized the older ultraviolet light to ensure their safety. And so it was a natural progression for someone to say, oh, well, we already know that is very effective. If you can now do it with an occupied space, this is perfect. So we are seeing a lot of uptake in the healthcare facilities. And not only mention that is, when we talk about a higher risk area, well, if people are coming down with any ailment, whether it's a common cold, flu, or a COVID, they would actually specifically go to those areas. So you're going to want to keep those areas clean. And of course, schools are are a big push for, some of the American Recovery Plan money that's now being added on top of the CARES Act and CRRSA. But we are aware that there are schools on bases, and we can provide a very effective role there. I think there's a new white paper that's really going to be great, that should be released in about the next week or two, that IUVA is putting out, that will show the efficacy against a whole host of different pathogens, particularly viruses in this first swing at it. And 222 is actually shown to be more effective than 254 for the exact reasons that Jamie pointed out about the protein absorption curves and things like that. And so, a lot of this is out there already and readily available in terms of researching it. And I guess with that, I'd be ready to pass this into the Q&A session.
Okay, sounds great. Again, greatly appreciate the presentation. We do have quite a few questions, so not sure on the timing how we'll do here, but I would think worst case we can coordinate getting questions answered after the fact. So first up, I'll pass this on and repeat the question. It was mentioned research 222 nanometer LED lamps have efficiency less than 1% today. What is the efficiency of an Eximer lamp at this wavelength?
So that's a good question. Yeah. So even Eximer lamps, which are the most efficient way of producing 222, are not super efficient. They're so most of the Eximer lamps that we use are typically around 6 to 8% efficient. And I think one thing that has to be kept in mind is that most UV UV LEDs or UV lights in general are pretty inefficient. So let's say a typical UV LED in the, say, 260 to 270 nanometer range, they are pretty generally less than 10% efficient. So although Eximer lamps are only 6 to 8% efficient, that's actually pretty similar to the UV LEDs that are commercially available now. So, so it doesn't sound very efficient, but it's actually way more efficient than 222 LEDs in any case.
Okay, thanks. Next question. What FDA hurdles are in the way of allowing widespread usage in public spaces?
Yeah, I can cover that one. So interestingly enough, this is not regulated by the FDA for a very good reason. The far UV is not a cure for COVID. It doesn't treat the person, but what it does is it treats the particles or the pathogens that are respirated into a space, either into the air or on the surfaces. And as a result, when talking to the FDA, they said, well, all right, describe what you do. And we kind of went through that whole thing. And they said, okay, well, you're not a medical device because your intent is not to be used on people, even if you could potentially hit people. But you're regulated by the Environmental Protection Agency, by the EPA. And then the manufacturers need to get registered with the EPA, and they have to, of course, abide by any FIFRA labeling requirements, which talk about, levels of safety or efficacy in how they're used there. So, yeah, the FDA. Now, you could be regulated by the FDA. However, if you were to say that it's intended for use on people, like if it was being used for ulcers, and we actually have looked at some of those things as well, or battlefield wounds. I think it's 87% of the people who suffer an injury in battle don't die from the actual from the bullet or the shrapnel, it's the disease that follows, or it's the infection that follows. And so we have looked a little bit at that, but I think right now most of the industry is focused on non-medical applications. I think there are medical applications for this that some people may eventually target, but the use cases that we're talking about here of cleaning the air and surface around you to prevent the spread of an infectious disease are not an FDA regulated item.
Okay, again, thanks. Next question. I think this one's oriented towards the higher energy 222 nanometer. Will it have any negative impact to the stratum corneum, which is burning it?
I'm sorry, could you repeat that? It was very difficult to understand. You're kind of breaking up.
Yeah.
Sorry about that. Hopefully this will be clear. Again, the question was oriented towards, will the higher energy 222 nanometer have a negative impact on the stratum corneum, such as burning it?
Oh, I see. Oh, okay. So the question is, does it harm your outer skin by being absorbed? And the answer is no. No. In fact, it does not harm your outer skin, the fact that it is absorbed, because the actual total energy there is no different from, let's say, the amount of energy that you would get from other light. So in other words, ordinary green light or ordinary blue light is also absorbed by your skin, and that's not harming you. So the answer is no. It does not heat you up. It does not harm your stratum corneum, and in fact, in general, it's also not harmful to materials. So Boeing's also done quite a bit of work on does this damage materials? So let's say materials on aircraft, and the answer is no. It may cause some discoloration of some materials, like most UV does cause discoloration of or maybe cause fading or whatever of the colors, but it does not penetrate deep into structures and whatnot, so it does not affect their mechanical properties. So, and the same is true for you and your skin. It doesn't, it's absorbed by your skin, but it doesn't harm your skin.
Okay, thanks. Next question. What are the absorption mechanisms for the 222 nanometer photons?
So again, I'm having a hard time understanding you. Could you repeat that again?
Apologize. Again, hopefully this is coming through clear. What are the absorption mechanisms for the 222 nanometer photons?
So if I understood you correctly, you're wondering what are the absorption mechanisms for 222 photons? So in the as with all photon absorption mechanisms, it's literally molecular, and so in the case of both protein and DNA, the 222 nanometer photons are highly absorbed, and so in the case of 254, it is less absorbed in protein. So I guess are they looking for a quantum mechanical answer? I'm a little lost by the question, actually.
Here's a follow-up intermediate. Hopefully you're getting this clear. Are any photochemical reactions driven in the dermal surface, or is it ultimately converted to heat / temperature increases?
Oh, I see. Okay. So in the case of let's say interaction with the DNA, so in the case of interaction with the DNA, what actually happens is the photons interact with the DNA and cause the breakage of particular bonds. And in the case of, which is typically in thymine, actually, and in the case of protein, the 222 nanometer UV actually interacts with peptide bonds, and so in the case of let's say your skin cells, it is going to interact with your outer skin cells and cause the breakage of peptide bonds in the membrane of the stratum corneum. But that, because those cells are already dead, it doesn't really change them, because although some protein bonds in the cell walls of your stratum corneum have been altered, it hasn't really changed them because they're already dead. If those cells were live, then it could damage the cell, but again, in the case of humans, the stratum corneum absorbs almost all the light.
Okay, thanks. Next is, has there been any evaluation on the use of other gases such as argon or xenon? And then a follow-up, why was krypton gas chosen for use in the Eximer lamp?
So yes, you can use argon or xenon or pretty much almost any inert gas for Eximer lamps. And what is the case there is that you're looking for particular molecular combinations, and in Eximer lamps you pretty much always use at least one of the gases is an inert gas. And that is because when you have an inert gas in there, the molecules created by essentially the lightning strike inherently want to decay immediately, because an inert gas does not want to be in molecular form. So, in fact, one type of Eximer lamp is a xenon lamp, so it's pure xenon, which actually creates essentially a xenon 2 molecules, which immediately decay, and that it's the wavelengths associated with the decay that matter. And so the only system that we're aware of, and there may be other systems, but the only system that we're aware of that creates a strong signal of 222 is krypton and chloride. So that doesn't mean that there are potentially others, but we're not aware of them.
Okay, thanks. Next question. What power densities are required to achieve the desired disinfection thresholds?
I may take that one. So I guess the disinfection threshold, so if you're talking about the threshold being the threshold limit value, and that's very interesting, because even at the 23 millijoules per centimeter squared, what that's more or less telling you is if you can get a 1 log disinfection with 1 millijoule per centimeter squared, it's more or less telling you then that you can get 23 1 log reductions, throughout that 8-hour period. And that 8-hour just resets every 8 hours. So, basically 3 times that much over the course of a day if it was a 24/7 application like a air traffic control tower or something like that. But that's where it is today. But when it then moves to 500 millijoules, or I think the notice of intent to change that's been already announced by ACGIH is, upper like 493 or 7 or something like that. You're now talking about, really repeated ability to, create those levels of disinfection really in under a minute, throughout the course of the day. So I think if that's the question in terms of how much are we able to safely do right now under the existing standards and under the standards that we expect within the next, 3 to 6 to 12 months, those are the kind of levels that we're talking about. So, and the higher that threshold goes, effectively, we have the tools to deliver the higher power thresholds with the lights. If anything, what we do right now is we use programming to just turn them off and on to deliver, a customized amount to any given space based on the ceiling height. And that's how it's delivered. But it will get to a point where it's a little bit more like just a purely continuous disinfection instantaneously. The second it does come out of your mouth, the particle, it is started to be treated and disinfected right now, and it's only going to get faster in terms of how much it can.
Okay, thanks. We're about 5 minutes after the hour. What I'd like to do, if you're amenable, Jamie, PJ, I can keep going through the questions, but certainly we would want to get written responses and ideally post them to the briefing. Is that something we could work? And do you?
Sure.
Does it work to continue then going through we've got several more questions, so it's probably going to be another 15 minutes maybe.
Sure.
Yeah. Let's go for another 15 minutes and see if we can't get them done.
Okay, will do. Next is a consideration aspect. His question with, might these also be useful for treating wounds on the battlefield?
Yeah, actually, that is. Yeah. I'll touch on this one, PJ, for just. Yeah, so that's an application that we have looked at, and I think the answer is yes. And we don't have a lot of data on that, but yes, I think that the wand product that PJ showed would certainly be appropriate for that kind of thing, and I think considerably more data would need to be collected before you would take that live onto the battlefield, but it does seem like that is a possibility. Yes.
We actually had designed a wand earlier under a NASA contract that was given an X-Tech Search Award by the Army for exactly that concept. It didn't get deployed, but it was kind of an earlier stage. It was really prototype level, and I think with the new additional information now, it's certainly something worth re-exploring.
Thanks. The next question folds around overall cost effectiveness. The question is looking at self-decon of surfaces versus disinfecting the surfaces, potentially repeatedly at a significantly higher cost. So again, anything with respect to overall cost effectiveness of the UV disinfection versus self-deconning?
Yeah. I think I touched on that briefly before, with the concept of just somebody wiping down surfaces all the time can be anywhere from 50 to 100 times more costly than the daily cost of, providing, this far UV solution. A light will last, a good 1,000 days, depending on the cycling that you're using. And so, if you simply extrapolate what the costs of, if you had a person who was wiping stuff down every day for 10 days at minimum wage, that'd be about $100 a day. So over 1,000 days, that would be upwards of $100,000 to wipe stuff down versus the cost of this equipment, which is, anywhere from $2,500 today and actually, reducing as the economies of scale continue to grow. So it's considerably cheaper. And more importantly, the hard thing is in their space, it's this invisible threat. We don't know when it's there. You can't smell it, you can't see it. So having a persistent continuous disinfection, I think, is also far more effective. If you knew it was there, then you could have, much easier stay away from it, but you don't. So I think this is a more comprehensive solution and at a fraction of the cost, actually.
Okay, thanks. The next one folds to basically kind of the rhetorical, how clean is clean? The individual is noting that they've tried to get express I guess, QC checks from DHS or HHS. So ultimately, when you say something is disinfected, to what level? The interest is to determine some kind of testing to determine to what level is the contamination complete, disinfection complete.
Sure. So that's an interesting question. And what is interesting with a far UV source is, in theory, if it's continuously disinfecting, it will continue taking it down. So you may have that, 1 log reduction in, X minutes, and then another X minutes from them, the same interval, you'll have another log reduction. So in theory, it doesn't necessarily stop at 99%. It'll just keep adding nines in a log reduction, 99.99, et cetera. In terms of how clean you need to be to prevent infection is a very challenging question, because we ultimately, now you're referencing the relative vulnerability of different people's individual immune systems. And so while we don't know those, by knowing what we do know is, we do know exactly at any given inch square or cubic inch in a room exactly how much disinfection we can provide against a given pathogen. And so it's that our goal is to just reduce the viral load, so that, perhaps we not only keep the people, from catching it who are usually pretty bulletproof to getting illnesses, to all the way to the most vulnerable of those. If it's a medical situation where somebody's immunocompromised from the medicine they're taking or something like that already, if you can continue to reduce that viral load as much as you can, that would be there. But I don't think that's if I understand the question right, I don't think it's something that the DHS or the HHS could specifically determine in terms of what viral load is. I know they have done some studies that have tried to estimate that, but I don't think there's a consensus around it with SARS-CoV-2 at this point.
Okay, thanks. Next question, is there a wraparound application available which could address pathogens that are not in the line of sight? Or would this challenge require the installation of additional fixtures as a solution?
Well, the wand that Jamie showed, that Boeing developed, is a good example of one that addresses I think this question is really addressing potential shadowing with line of sight. And so in that case, the wand waves over a surface, and that allows it to kind of get hit in all the nooks and crannies, let's say, in that cockpit example of that. But as far as treating under tables or desks or things like that, I would go back to the concept of how the pathogens actually, what surfaces they end up falling to. And in almost every case, it's going to be the top of whatever the surface it falls to, whether that's a desk or the floor or a chair or a person. And that's what makes the overhead fixture so effective, is those typically are within the line of sight of the tops of the surfaces throughout a room. And in some cases, you won't have one light in the room, so you will be hitting things from different angles as well. And so it may not cover everything, but I think it's going to cover the majority of what the risk profile would be in a respiratory infectious disease.
Okay, thanks. Next question is oriented towards the prospect of the 222 nanometer UV lights creating ozone, with respect to ozone being potentially problematic to health. So again, the ultimate question is, does the 222 nanometer UV create ozone as a byproduct?
Yeah, let me touch on this one, PJ. So the short answer is yes. 222 does create a small amount of ozone, but it turns out, at least in the Boeing studies, that at the even with a very, very powerful wand, so let's say when we've used a very powerful 222 wand that is not even sealed on flight decks. We stay below the ozone regulatory limits. And in the case of the type of systems for these persistent UV, those systems actually generate almost no ozone. So when we do testing of a one of these smaller systems that is let's say permanently installed, or that's its intention in any case, we see something in the neighborhood of maybe 1 part per billion of ozone generated on a as a compared to the background. And to put that in scale, you're allowed to have 100 parts per billion on a continuous basis, on a 24/7 basis, and you're allowed to have 300 parts per billion on a temporary basis. So 1 part per billion that's pretty much background. So effectively, there's no ozone issues whatsoever.
Okay, thanks. Next question is, most modern polymers are not UV stabilized like exterior grade polymers. Will we have to replace all of our interior polymers if UV begins to be widely used?
So did I understand the question correctly? Are they wondering what's the effect of 222 on polymers, or what was the question?
Again, it's acknowledging that there's a concern with respect to most modern day polymers with respect to UV breaking them down. So the question is, will we have to replace all of our interior polymers if UV begins to be widely used?
Okay, yeah, actually, we've studied that quite extensively. So Boeing has studied this quite extensively because we're looking at using 222 on aircraft interiors, and aircraft interiors have, of course, a lot of polymers in them. And so what we found is that actually, in terms of damage, structural damage to polymers, so their ability to withstand to meet their structural loads, and their ability to resist fire and other important structural mechanical properties, 222 appears to have no effect on that whatsoever. And the reason appears to be the case that because 222 does not penetrate very deeply into polymers, so keep in mind that, let's say, 222 is likely to penetrate only a few microns into the polymer, so probably less than, say, 10 microns into a polymer. So to sort of put that in scale, just a typical paint coating is going to be more than that, right? So the really even lifetime exposure to 222, it may cause, let's say, the paint to fade, but it is not going to cause structural damage to the underlying polymer structure, no.
Okay, thanks. Next question. This is first an acknowledgement, then followed by a question. This technology can eradicate most pathogenic disease when implemented in all habitable spaces. A major national initiative to reduce the cost and ensure widespread availability of Eximer and solid-state light sources is imperative to eliminate current and future pandemic and all bacterial disease. Have the top tiers of UV and all government agencies been briefed on this?
Well, I would say that part of this webinar is to help spread awareness. Awareness is the most important thing, I think, for this technology right now, and hopefully, I believe this will be recorded and stay available. But we've been doing our best to try to to bring awareness to this, and it has reached several layers. Although I know it's installed at the top tiers of the Pentagon, so I think that kind of starts to address, I think, where you're going with it. But has it really been penetrated? No, we're just at the very, very beginning. And so awareness is key. I hope you all spread the word.
Yes, correct. That is an objective of the webinar, and it is recorded. So
Awesome.
hopefully the word will get out. The next question is 222 nanometer light safe to shine in the nose and mouth, or just the eyes?
So again, I think that the short answer to that is it's possible that it is to shine, it's safe to shine into the interior of humans, but we don't have specific data on that. What would be the case is that it would not make it past the surface cells, so it would penetrate whatever cells were on the actual exterior of the inside of your nose, or the exterior cells on the inside of your mouth. So it would penetrate into that very first cell layer, just like it does, penetrate slightly into the stratum corneum. And whether penetrating that very outer cell layer causes you any harm, I don't know. We haven't studied that. So I think the answer is probably it's safe, or at least reasonably likely that it's safe, but we don't have that data, so I can't say for sure.
Well, and I would add on to that the incidence. So typically the far UV light will be strongest directly in front of wherever that lamp is pointing. And so in, let's say, a ceiling application, it's pointing straight down. So to get into your nose in like that kind of an application, you'd probably have to be standing on your hands upside down somewhat. And so and I'm not trying to be flippant about that. There's actually quite a bit of study that was done on upper air UV disinfection beforehand, where they kind of note that even with the eye, for a ceiling mounted unit or something from up high, the angle of incidence or the angle of dispersion is so low, the relative intensity of the light is so low at a part where it would get hit, and the actual eyelid actually shelters the eye mostly from that light, unless you were to just stare up at it for an extended period. And even in that case, the fixtures are designed to maintain that safety. So that's kind of the first half of it. The other aspect is, again, the fixtures out there right now are not designed for use on people or in people. It's more of incident exposure. And so if you were going to be sticking, a far UV light in your nose or your mouth on purpose, like maybe in a dental application or some kind of medical application, that's when you would trigger an FDA approval, and all of those studies would potentially be required.
Yeah. So let me add something to that, which is that, I think that in the case of, let's say, the incidental amount of light that might enter your nose or enter your mouth from a lamp
Right.
that was ceiling, that would be no issue whatsoever, because even under the current TLV, which doesn't even include any of the recent safety data, you would be allowed 23 millijoules. So so even the 23 millijoule number, would not be accumulated in your mouth, even if you held your mouth open, to the light for quite some time. So from a standpoint of just normal exposure to a light mounted in the ceiling, that'd be no issue whatsoever in the nose or the mouth.
Okay, thanks. Again, we've kind of went beyond the 15 minutes, but I'm going to throw out, I think, two more questions here that are fairly short. That probably would require a fairly short response, but we still have well over a dozen more. I'm going to say probably best to cut it off after that, and then we'll get written responses and post them out, or again can distribute them to the attendee list. So one quick short one is the one lamp can cover how many square feet? And the next question is it effective, equally effective for all disinfection as for, or is it equally effective for air disinfection as it is for surfaces?
I can take some of that. It depends on the fixture in terms of how many square feet. There are different powered lights, much in the way, if you got a light bulb for your lamp, you could have a 40-watt lamp light bulb or a 100-watt, or equivalents these days. I guess they do it in lumens because it's more LEDs than anything right now. So that will determine the amount of square feet. A lot of what currently is out there are anywhere from either a regular ceiling, under 11-foot ceiling would probably be up to about 250 square feet. And again, that's a relative basis. There is an angle, about an 80-degree angle of dispersion. So it can cover everything in the room. It's just the further away you get, the less disinfection it's got because the intensity of the light changes. Almost like with a flashlight, if you hold it close to the wall, it's very bright in a very small circular pattern. And then the farther away you back up from the wall, the wider that light gets, but also the less bright it gets because it's basically going further out to the sides, the angle of dispersion. So that's the rough amount that a ceiling light could handle. But the lamps that are available now, like the ones that Jamie mentioned at Boeing, those are very powerful lamps, and they could cover much more. It's just a function of how they're applied, and the ceiling heights typically drive most of that. The difference between an 8-foot ceiling and a 10-foot ceiling is actually pretty significant in how wide that coverage is. As far as air versus surfaces, it has been proven, and some of the data that Dr. Brenner at Columbia has did quite a bit on the air side, and it is kind of an intuitive aspect that it's easier to kill something in the air because there are really no line of sight issues in the air unless it's smoky or something, unless there was a thick substance of something in the air, but it'd have to be pretty thick. On surfaces, however, it does depend on what the surface is. So if you have a smooth surface, like a metal table or a plastic surface or something like that, it's going to be very effective. If you have an organic surface, and we did a lot of testing under our NASA contract on different foods, looking at food disinfection and shelf life extension and whatnot. Turns out the surface of a food under a microscope is actually very porous and hairy and a lot of things like that. And so it can be less effective on some surfaces. So it varies quite a bit in surfaces. In air, though, it's an easier kill. Also, remember, the closer to the light you are, the more disinfection you're going to have. So presumably it's treating whatever surface it hits, but it's also treating all the air in between the light and that surface. So just almost by definition, it's getting more fluence or more dosage of the 4UV, in air versus at the surface, which is kind of the furthest length that it would be. Hopefully that touches on it. I don't know, Jamie, if you had any other thoughts.
Yeah, well, I guess what I would also kind of add to that is that so if the question is, what are the, how much light is necessary and how effective is it? So yeah, so it's just as effective on things that are in the air as it is on surfaces, if not more so. But also the different pathogens require different amounts of total ultraviolet energy to be effective at killing them. So I think the answer is highly dependent on the exact pathogen you're trying to kill, and as PJ said, essentially the range to the bulb and the power of the bulb itself.
Okay, greatly appreciate the time and responses, Jamie, PJ. I'd say at this point, we probably want to cut it off. It's 1:30 now, we've been 30 minutes over, and we could, I'm guessing, probably have about 15 more minutes to answer the remainder of the questions. So again, with your agreement, we will go ahead and coordinate getting those questions to you. If you wouldn't mind responding and, in writing, and we can get those out to the attendees and posted with the briefing as well.
Sure.
Sounds like a plan.
All right,
Thank you.
well, yes, thank you both very much. Appreciate everyone's attendance and time. And hopefully, again, getting, certainly this is an in vogue topic and has created quite a thought-provoking discussion. So, yeah, appreciate folks' attendance and look forward to hearing or seeing from you in future webinars or in various Information Analysis Center support efforts to the DS community. So again, thanks much for everyone's time. Take care, all.
All right. Thank you.